In this next chapter, we are going to look at multivariable functions. And multivariable functions are just functions that contain more than one variable. So instead of looking at things like f of x, we're going to look at things like f of xy or f of xyz. Okay? For a formal definition, a function of several variables is a real valued function f of x, y, z, etc. It's basically a rule that gives us a real number, which we're going to call f of that, from a sequence of independent variables. Okay? So for example, f of xy, this is a two-variable function. Here's our rule. It says that f of xy is going to be 4x minus 3y plus 7. And just like before, when we were asked to look at functions, one of the first things we did was evaluate them. And so here you're going to be asked to do the same thing. So if I want to evaluate f of 1, 2, this just means I'm going to plug in 1 for x and 2 for y, and then evaluate my rule. So here, I would say this is going to be 4 times 1 minus 3 times 2 plus 7, or 4 minus 6 plus 7, which is going to be 5. Okay? And same thing down here. If I want f of negative 2, 1, that means I'm going to plug negative 2 in for x and 1 in for y. So 4 times negative 2 minus 3 times 1 plus 7. So negative 8 minus 3 plus 7 looks like negative 4. Okay? And so again, it's a real valued function because the things that should come out should be real numbers. And everything I plug in should be a real number. Okay? We also have what we call functions of 3 variables, or 4 variables, or so forth. So in this case, we're looking at f of x, y, z. This is a function of 3 variables. And in this case, if I look at this, 2e to the x minus y plus 3e to the x plus z plus yz, we can see that this is a little bit more involved than the last function we looked at. Okay? Same thing if I want to evaluate this, f of 0, negative 1, and 2. That means, again, I'm going to plug in 0 for x, negative 1 for y, and 2 for z. So 2e to the 0 minus a negative 1 plus 3e to the 0 plus 2 plus negative 1 times 2. And so we can see here we'll get a 2e plus 3e squared minus 2. Okay. And again, even though that's not a pretty number, it is still a real number. And so there's our value for that function. A linear function of n variables is any n variable function that contains no products or no powers of the variables. So similarly to what we had in one variable sense. If we talked about a linear equation in one variable, we were looking at things where there were just x's, there were no products, there were no quotients, and there was no powers or roots of x. Same thing is true here. So if I'm looking at some function of n variables, my variables being x1, x2, etc., then I can look at my function in this fashion where it's some constant plus some constant times my x1 plus some constant times my x2, all the way out to some constant times my xn. And again, here, constants, we just mean some real number times those. It could be 0, it may not, but again, no powers, no roots, no fractions or products of these variables. So just like in the previous parts of the course, when we're dealing with functions of one variable, and you were asked to look at different representations of the function, we had 3 different representations. There was the numerical, the algebraic, and then the graphic representations. And so we're going to do kind of the same thing with functions of 2 variables. Now, when we look at functions of 2 variables, the first thing to keep in mind is it is really a 3-variable function we're looking at. If I say f of xy, I'm actually thinking z is going to equal f of xy. Just like in the one variable sense, there were really 2 variables we're looking at. When we said f of x, we really meant y equals f of x. So there's the 2 variables. Now, in the case of these 2 variable functions, f of x, y, you are going to be asked to do a little bit with the numeric and a lot with the algebraic. Some of your functions you are going to be asked to graph, but not many of them. So I'm going to, in this example, show you a little bit about how to graph some three-dimensional objects, but you're not going to be asked to do this on an exam. Okay? You will see it in the homework and on WebAssign. So let's start with the numeric representation. In the numeric representation, you're not always given a function. You're usually given information about the function. And in some cases, before, this looked like a t-chart. We had the x and the y, and we had kind of the t, where you pick some values for x and plotted values for y. In a two-variable system, meaning x and y, it's going to look more like this, a table, where in one instance, so each of the rows represents our values in terms of x, and each of the columns gives us the y's. So if I want to find a particular point, meaning, for example, 0, -2, there would be my function's value. Okay? And so one of the things you're going to be asked to do is, given a table or a representation like this, be able to come up with some of the function values. Okay? So here, if we look, if I'm trying to find f of -2, 1, again, this means -2 is my x and 1 is my y. So when x is -2 and y is 1, we are looking at the value 5. Okay? Likewise, if I look at f of 2, -1, I'm also going to get a value of 5. Okay? So here is my f of -2, 1. Here is my f of 2, -1. Okay? If I'm looking at f of 1, -2, again, that means x is 1, y is -2. Okay? You can also see that's 5. And then, lastly, if I look at f of 0, 0, so x is 0, y is 0, so I'm just going to get 0. Now, in some cases, your numeric representation can give you enough information that you could actually figure out the function, but you're not going to be asked to do that. Again, for these types, this is the extent of what you're going to be asked to do. Okay? If I'm looking at the algebraic side of the function, again, I'm going to be asked to evaluate, just like we saw in the last few examples. The difference now is I can actually do this algebraically. I can take my function, x squared plus y squared, and I can put in the values and actually evaluate. So here we can see f of -1, 2 means I'm putting in -1 for x and 2 for y, and then I'm going to square each of those to get my value. Likewise, if I do f of 0, 1, I'm looking at 0 squared plus 1 squared, which looks like 0 plus 1, or 1. And lastly, if I look at f of 2, -2, 2 squared plus a -2 squared, looks like 4 plus 4, or 8. Okay? And here, it may not be obvious, but you can see, kind of going back and forth between the numeric and the algebraic, I can actually see that I'm looking at the same function, just different representations. Okay? The last example is our graphic representation. And just like before, this means I'm actually going to look at a picture of what this thing looks like. So again, before we would take the points that we found and plot them on a x and y coordinate system. The difference now is, again, if I think of my f of xy as some z equals this function, then I'm actually looking at a three-dimensional coordinate system. Okay, so I've got my x and y that we normally have, but now I also have this third dimension z. Okay, and for some of these, like I said, it's not always apparent how to go about graphing these. And so the best way to think of this is if I'm looking at z equaling x squared plus y squared, I can do two of the dimensions at a time. And what I mean by that is if I let x equal 0 in my function, then I'm basically looking at z equals y squared. Okay? And so we know what this looks like. if I look at the graph where this is my y-axis and this is my z-axis, then I can see that z equaling y squared is just going to be a parabola. Okay? Opening in the positive z direction. Okay? And likewise, if y equals 0, okay, again using my function there, I can see that z equal x squared. And again, if I'm looking at my two-variable coordinate system, again, that's just a parabola. Okay? And so in both cases here, I'm looking at a parabola that's opening towards the z-axis. And so here I can think in my y direction, and the first thing I'm going to do is I'm going to kind of dot in my negative axes here. So if I extend my y-axis to the left, and I extend my x-axis into the board, then z equal y squared, I know is going to be a parabola in the y direction. Okay. And if I look in the x direction, so looking along the x-axis going into and out of the board, I'm going to have a parabola in that direction. Okay. And that's not so easy to see, but in this picture, what this is saying is, as I look at this, I'm going to form around the z-axis what we call a paraboloid. Okay, and so it's going to be kind of hard to picture here. Okay, but there is my three-dimensional. Let's see if I can make that a little prettier. There we go. My three-dimensional object. Okay, again, there's my axes coming up. Okay, and since some of these, like I said, you are going to be asked to graph them or at least get a picture of what's going on. And we can kind of see here, again, if I look at the two-dimensional cases, I can figure out what's happening in those dimensions and then apply it to that three-dimensional object. Okay. Now, what does this mean in terms of what you're going to be asked to do? On the homework, and possibly on an exam, you're going to be asked to do some point plotting of three-dimensional objects. And that doesn't mean actually graphing the entire picture like we did here. It just means being able to figure out where things, particular points actually lie. So for example, if I'm looking at my three-dimensional coordinate system and we want to plot the following points. Okay? So we want to plot the point, which I'm going to call A, 1, 2, 1. And we want to plot the point B, which looks like 2, 0, 3. And we'll do one more. We'll plot the point C. I guess I need my closed parenthesis on that point. We're going to plot the point 1, negative 1, 1. Okay. So on these, in order to plot the points, again, I just need to orient myself on these axes. Okay. And in some cases, again, I may need the negative axes, which I'll just kind of dot in there with some dotted lines. Okay, so my first point, 1, 2, 1, it means I'm going to go 1 in the x direction. Okay, so 1 in the x direction, and then I can think there's my x equals 1 line. Okay, 2 in the y direction, so from that point I'm going to go 2 units over. And then 1 in the z direction. So again, from this point, I'm going to draw in a new z-axis and go 1 unit in that direction. Okay, so there would be my point A. It almost looks like it's on the y-axis, but it's actually in front of it and above it a little bit. Okay, for my point 203, same thing. I'm going to start with my x. I'm going to come out 2 units. I can think of dotting in my new x equals 2 line. I'm going 0 in the y direction, so I haven't left the x-axis. Okay. And then I'm going to go 3 units in the z direction. So there's 1, 2, and 3. Okay, so there's my point B. And again, if I look at that, it's going to be in line with the zx plane, because I haven't moved any direction in the y, and there would be my point, 3 units above the x, 2 units in front of the y, 2 units in front of the z. Okay, for my last point, 1, -1, 1, okay, this one, again, I'm going to start on my x equals 1 line, which is that blue horizontal line we drew. I'm going to go -1 in the y direction. So now, from here, I'm going backwards on this line 1 unit, which is going to be over in here, and then 1 unit up. So from there, again, I'm going to draw in my axes and go 1 unit up from there. So there's my point C.